This video is going to take you through Chapter 2, Section 4, 5, and 6. So we start with properties from algebra. And the first are properties of equality. The first one is the addition property. And the addition property says if A equals B and C equals D, then A plus C equals B plus D. Basically what this means is if you have a statement that's originally true and you add something that was equal to both sides of the equation, then that's your addition property. It keeps the equation balanced. The subtraction property says the same, but subtraction. If A equals B and C equals D, then A minus C equals B minus D. So if you take a statement that is already equal or balanced, and then you subtract an equal value from both sides, then you keep that statement balanced. The multiplication property says if A equals B, then AC equals BC. This time you're multiplying the same thing on either side of the equation. And the only rule here is that C cannot be 0. Obviously, if it's 0, it cancels everything out. And the last one, the division property. If A equals B, then A divided by C equals B divided by C. So now we're dividing both sides of the equation by the same thing. And again, C cannot be 0. This time it would be undefined if I divided by 0. Okay, continuing with our properties of equality, here's some more. The next one is the substitution property, and that says if A equals B, then either A or B may be substituted in for the other value in any equation or inequality. For example, if 2A equals 10 and A equals B, then in place of that A, I could put the B. So 2B would equal 10. The reflexive property says anything equals itself. So A equals A. If it helps to remember, like if you're thinking about your reflection or you're looking at your reflection, you're looking back at yourself. Anything equals itself. Symmetric property is next. If A equals B, then B equals A. So the order just reverses here. Transitive is an if and then statement. So if A equals B and B equals C, then I can join A to C and say A equals C. And lastly, on this slide, the distributive property, and it has two parts, distributive sum and distributive difference. So if you have a sum inside parentheses and then something being multiplied to the front, you can distribute that value into both parts of your sum. And just like that with the difference, you have a difference inside parentheses and then you have the value on the outside and you can distribute that value to each of the parts on the inside. These properties, so we learn them in algebra, but they actually all get applied to angles and segments. So we can say the reflexive property for a segment is any segment equals itself. The reflexive property for an angle, any angle equals itself. The symmetric property, remember this is the reverse of the order. So if the segment DE equals FG, then FG also equals DE. And for an angle, if angle A equals angle B, then angle B equals angle A, just reversing the order there. Lastly, transitive also works for segments and angles. If AB equals CD and CD equals EF, then remember transitive says join the two together, eliminate that CD and join the two together, AB would equal EF. And for an angle, if angle A equals angle B and B equals angle C, then I can join A and C together and say that they are equal to each other. All right, example 1 says to justify each statement with a property from algebra or a property of congruence. So if I'm going from the if to then here, in 1, if AB equals CD and then CD equals AB, this is your symmetric property. For 2, 3 times x plus y in parentheses equals 3x plus 3y, we distributed there, so this would be the distributive. And specifically of addition here. For 3, if 2a plus b equals 24 and b equals 4a, then 2a plus 4a equals 24. So we just took our value of b and replaced it by what it equals, and that is And for if x over 3 equals 12, then x equals 36. So to get from the if to the then, this time we multiplied by 3 on both sides. And 12 times 3 equals 36 tells me this is the multiplication. And we do property of equality here. So multiplication, subtraction, division, and addition, we say property of equality like that. All right, example 2 says to justify each step. So in this process, you're actually solving an equation and you want to justify how you got from the step before to where you're at. So this first one is going to be given to you because that's the problem that literally is given to you. Then from that step to the second step, you got rid of the denominator here, so we multiplied by 3. This is the multiplication. Property of equality. C, we went from here to here, and we distributed that 3. So this is distributive. In D, comparing C to D, the 12 moved over here with the 2, so we added 12x to both sides, and that's the addition property of equality. And E, from D to E, we divided both sides by 14, so this is the division property of equality. All right, example 3 takes it one step further and it gives you the equation and asks you to solve it and then justify the steps. So here we're going to do all the work. In the beginning, we take our original, 3x plus 2 equals 23 minus 4x, and that reason is given. Now, there's a couple different things you can do here. You can either subtract the 2 from both sides or add the 4x, and it doesn't matter which order you do that as long as you eventually do both. So let's say I'm going to add the 4x this time. So the next statement would be 7x plus 2 equals 23. And we added, so this is the addition property of equality. Now from here, I'd subtract the 2. So the next step would be 7x equals 21. Subtraction property of equality. And the next one, we would divide by 7. And I'd get x equals 3, and that's the division property of equality. All right, example 4, solve for r in the formula and then justify your steps. So it's still solving. We're going to start with a given formula. So A is given. And the goal is to isolate r. So there's 2 ways to do this. One, I can distribute the p in. So I'm going to do this 2 ways. This would be pr plus p times 1, which is p, equals n. And that would have been distributive. Then I could have subtracted the p, and I would have gotten PR equals n minus p, and that's subtraction, property of equality. And then lastly, I could have divided both sides by p, and I would have gotten r equals n minus p over p, and that's division. Now, I also could have done it completely different order, but still correct. Start the same way. PR plus 1 equals n, and that's given. I could have divided both sides by p. R plus 1 equals n over p, and that's division property. Then I could have subtracted the 1. And that's subtraction, property of equality. So in both of these, we isolated the r. On the left, n minus p over p could be simplified to n over p minus 1, but you could have left it either way. All right, example 5 says you reflect the beam of a spotlight off a mirror lying on a flat stage as shown. Determine whether the measure of DBA, so DBA is this whole angle here, equals the measure of EBC. EBC is this whole angle here. Because 1 and 3 are congruent, and you can give it a value if you need it. Like, let's say these are both 60 degrees. The value of the angle that they share, it's the same angle that you would add to both of those. So because we know all three of these have to add up to 180, this could also be 60 degrees. They didn't all have to be the same though. And this 60 plus 60 would have equaled this 60 plus 60. So yes, if I needed to show proof, I could have said angle DBC is equal to angle ABE, and that's given because that's in my picture. Then I could have said angle 2 equals angle 2, and that's reflexive because anything equals itself. And then I could have said angle 1 plus angle 2 equals angle 3 plus angle 2, because I could have also said this is angle 1 and this is angle 3. And that's the addition property of equality. Then I can say angle 1 plus angle 2 equals angle BCE, or this order here, EBC. And angle 2 plus angle 3 equals angle DBA, which is this angle here. And that's the angle addition postulate. So then I can say angle EBC is equal to angle DBA, because if 1 plus 2 equals 3 plus 2, then I can put this in place of the 1 and 2, and this in place of the 3 and 2, and that's substitution. So this is what a geometry or geometric proof looks like. We'll eventually get to these in the next couple of sections, but it's a breakdown of reasoning based on picture or information and justifying your steps. All right, chapter 2, section 5 is proving statements about segments and angles. So this is probably everybody's least favorite part of geometry, and it is called a two-column proof. So a proof is somebody explaining why something is true. It is always going to be true, unless it says, is this true? But if it normally just says, prove this is true, then it is true. You just have to explain it using the properties and rules and theorems from geometry. So by definition, a proof is a logical argument that shows a statement is true. There are various formats. You could either do a flow chart in which you almost have like bubbles. One leads to this one leads to this one, this leads to this. Like it's almost like a map. You could have a paragraph proof where you literally use words to describe the entire thing. Or the most common is what's called a two-column format, and that is this. There is 2 columns. So there's a line here. The first column is your statements. The second column is your reasons. Under your statements, you're going to write either the given information or the result of applying a known property or fact. And on the right, you're going to put the reasoning for each one, kind of like we just did in that last example from 2-4. These are what is acceptable to be used as a reason in a proof. The given information, that should say given information, and this can be from a statement or from a diagram. Definitions that we know about segments or angles, properties, postulates, and theorems that are previously proven. A theorem is a statement that can be proven. So somebody before our time learned about a lot of different shapes, objects, segments angles, and their measures, and they came across these rules, and they call these rules theorems. So they had a theory, they thought this was true all the time, and then they eventually proved it that way. And they use deductive reasoning to prove them. So not patterns, but actual fact. The first theorem, and it's got a number, it says theorem 2.1. All that number means is it's the first theorem in chapter 2, so the number here is not important. The name of it this time is Properties of Segment Congruence. And basically it says segment congruence is reflexive, symmetric, and transitive. So instead of just saying that AB equals BA, you can also say segment AB is congruent to segment BA. And then theorem 2.2 is the properties of angle congruence, which says angle congruence is reflexive, symmetric, and transitive. So I can say the measure of angle A is congruent to the measure of angle A, and that would be reflexive. I can say segment AB equals segment BC then segment, or is congruent to, then segment BC is congruent to segment AB, and that would be symmetric property of congruence. So the chart that we had in 2.4 where we talked about all the equals, right, all the properties of equalities, now we're doing with the properties of congruence. So notice all the symbols just changed. The reflexive property still says anything equals itself, so any segment in this case would be congruent to itself, and any angle would be congruent to itself. Symmetric is the order, so if DE is congruent to FG, then FG is congruent to DE. And if angle A is equal to angle B, then angle B is equal to angle A. And the transitive property, your if and then statements, if AB is congruent to CD, CD is congruent to AF, then AB is congruent to EF. And if angle A is congruent to angle B is congruent to angle C, then angle A is congruent to angle C. So the only difference here is that we're using congruence instead of equality. All right, so now we're going to use these properties in a two-column proof. So there's two kinds of two-column proofs, one and where it's partially filled out, like this one, and then one where it's completely blank. We're going to baby step our way to the completely blank ones. So if you look at the given and the proof, because you always want to start there, the given says AC equals AB plus AB. So if I look at the diagram, I have AC, which is this full segment. It says AB plus AB. So I'm not using this segment yet. I am given that AC is made up of AB plus AB. And that means that this first statement is given. The second statement says AB plus BC equals AC. Now that's based on this picture. AC is that whole thing. AC is equal to AB plus BC. And because we're saying that the segment is equal to the sum of its parts, this is the segment addition postulate. So segment addition postulate, if you want to write it all the way out, we're going to eventually abbreviate it as SAP. 3 says AB plus AB equals AB plus BC. Well, if I look back to what I was given in the beginning, AB plus AB is equal to AC, and AB plus BC is equal to AC. So if two things equal AC, then I can take one of them and substitute it in. So if I took AC and I substituted it by AB plus AB, that property is the substitution property. And then this last thing says AB equals BC. So if I compare 3 to 4, I had AB plus AB and AB plus BC, and I went to this step by eliminating AB from both sides of my statement. And eliminating or subtracting would be your subtraction property of equality. Let's try another one. Example 2. Now my given says M is the midpoint of AB. So M is the midpoint of segment AB. And I'm trying to prove two steps. The first one is that AB equals 2 times AM. And the second one, AM, is 1/2 of AB. So let's take it step by step. First thing is given to you. Second thing says AM equals MB. So I know this is true based on the definition of the word midpoint. The midpoint says the point in the middle or the point that cuts these into two congruent parts. So that is literally the definition of a midpoint. Three, the only thing that changed from 2 to 3 is that the congruent symbol went to become an equals and the actual segment symbol went away. So this, going from congruence to equals, or the other way around, because you're going to see it both ways, is the definition of congruence. Sometimes it will say definition of congruent segments. Sometimes it will just say definition of congruence. I would have taken either one. Now 4 says AM plus MB equals AB. So this didn't come from anywhere before it, but if I look at my segment, AB is the full segment, AM is part, and MB is part. So we took our full segment and we cut it down into the two parts, which is segment addition postulate. Then in 5, the only thing that changed from 5 to 4 is that MB became AM. Well, the only way that happens is if AM equals MB, and it did. We said it in step 3. So we just substituted AM in place of MB, which means this is the substitution. Now looking at step 6A, which is the first thing we're trying to prove, it says 2AM equals AB. So we basically just took these two AMs and we put them together. We added them together or combined like terms. Now, if we had added to both sides of the equation, then it would have been the addition property of equality. But we didn't add to both sides. We just simplified the one side. So this statement is actually just simplify, or the reason for that statement. And 7, to go from 6 to 7, we divided both sides by 2 or multiplied by a half. So technically it's multiplication because we're multiplying by the half. But honestly, if you had said division there, I probably would have given it to you. All right, so here's some tips. Obviously, 2-column proofs, we did a little bit. In a proof, you want to make one statement at a time until you reach the conclusion. Because you make statements based on facts, you're using deductive reasoning here. Usually the first statement and reason pair you write is given information, but it doesn't have to be that way. And here's another example. So this one, the proof of the symmetric property of angle congruence. It says you're given angle 1 equals angle 2, and you're trying to prove angle 2 equals angle 3. So if angle 1 is congruent to angle 2, then that means the measure of angle 1 equals the measure of angle 2, and that's the definition of congruent angles. We can switch the order here and say the measure of angle 2 equals the measure of angle 1. The switch of the order is the symmetric property. And then we can go back to congruence, and that's the definition of congruent angles. The good news is you don't have to do that anymore. You can go from one to the other, and you can have your reasoning be symmetric. All right, last section in this video, and that is chapter 2, section 6, prove angle pair relationships. So we're going to learn some more about some pairs of relationships of angles. We're going to also look at a flow chart and a paragraph proof. So remember, the flow chart or flow proof uses boxes and arrows to show the flow of a logical argument instead of the 2 columns. And a paragraph proof presents the statements and reasons of a proof as sentences in a paragraph instead of a step-by-step process. Theorem 2, 3, remember in order, the number, not important, but the name of it is right angle congruence theorem. And what it says is that all right angles are congruent. Now, if you forget the name, if you don't know right angles congruence theorem, you can simply write out all right angles are congruent. All right, here's a flow chart. So this says, or flow proof. This says, use the given flowchart proof to write a 2-column proof of the right angles congruence theorem. The given is angle 1 and angle 2 are right angles, and the proof is angle 1 is congruent to angle 2. Here's the flowchart proof. We started with the given, which you'll just put like in a box or a bubble underneath it, the reason. So angle 1 and angle 2 are right angles. The arrow tells you which direction to go. Step 2, the measure of angle 1 equals 90 degrees. The measure of angle 2 equals 90 degrees, and that's the definition of right angles. The arrow tells you which direction to go. The next bubble is the measure of angle 1 is equal to the measure of angle 2. That's the transitive property. You went 1 equals 90 and 2 equals 90, so 1 equals 2. You could also use substitution here. And the arrow tells you where to go. The angle 1 is congruent to angle 2, definition of congruent angles. So if you look ahead to the next slide, it's started for you. On the left are all your statements. So the first one says angle 1 and angle 2 are right angles. This would have been given. Step B says the measure of angle 1 equals 90 degrees. The measure of angle 2 equals 90 degrees. And this would be the definition of right angles. C, the measure of angle 1 equals the measure of angle 2. Actually, this would be congruent. No, sorry, that is equals. And that is the transitive property of equality. Or I would have taken substitution on that too, because you're substituting in for a value. And then angle 1 is congruent to angle 2, and that's the definition of congruent angles. So one proof done 2 ways, flow proof and also 2-column. All right, next theorem is theorem 2.4. Again, number not important, but the name is congruent supplements theorem. It says if 2 angles are supplements to the same angle or to congruent angles, then they are congruent. So in this diagram, if angle 1 and angle 2 are supplementary, and angle 3 and angle 2 are supplementary, then angle 1 equals angle 3. Now, if you actually looked at values, if I said 1 was 60 degrees and 1 and 2 are supplementary, that means that 2 would have to be 120 because they have to add up to 180. And if 2 and 3 are supplementary, then that would mean that 3 has to be 60. And then I can say 1 equals 2 because they're both 60 degrees. But now I don't have to go through all that work. I can use congruent supplements theorem as that reasoning. This one, example 3, prove congruent supplements theorem. So prove that 2 angles are supplementary to the same angle, are congruent. Given 1 and 2 are supplements, and 3 and 2 are supplements. So this is step 1, given. 2, the measure of angle 1 plus the measure of angle 2 equals 180. The measure of angle 3 plus the measure of angle 2 equals 180. We know this because we know what supplements means, which means that this is the definition of supplementary. Three, the measure of angle 1 plus the measure of angle 2 equals the measure of angle 3 plus the measure of angle 2. So we took these 2 statements that were both equal to 180 and we set them equal to each other. We substituted 1 in for the 180, and so this would be substitution. And for 4, from 3 to 4, we eliminated the measure of angle 2 from both sides. That's subtraction. And we went from the measure of angle 1 equals the measure of angle 3 to the measure of angle 1 is congruent to angle 3, and that is the definition of congruence, or congruent angles. All right, theorem 2.5. Now we did congruent supplements theorem. This is congruent complements theorem. So the same kind of theorem, the only difference is instead of supplementary, we're talking about complementary. If 2 angles are complements to the same angle or to congruent angles, then they are congruent. So if angle 1 and angle 2 are complementary and 3 and 2 are complementary, then 1 equals or is congruent to angle 3. If 1 and 2 sum to 90 and 2 and 3 sum to 90, then 1 and 3 are congruent. Next up, linear pair postulate. This one's pretty popular. So the linear pair postulate, or postulate 2.8, the name is more important, says if two angles form a linear pair, then they are supplementary. So if angle 1 and angle 2 form a line, or the exterior sides of those angles form a line, then they are a linear pair. And if they are a linear pair, they are supplementary. And if they are supplementary, they add up to 180. The linear pair postulate tells us all of that. Vertical angles are another wildly popular topic in geometry, and the vertical angles are the two angles such that the sides of one angle are the opposite rays to the sides of the other. So angle 1, if I extend angle 1 and I extend the other side of angle 1, it forms angle 3. Those two are vertical. And 2 and 4, if I extend the sides of 2, it makes angle 4. Those are vertical angles. Now we know the definition, but we're reminded of the definition because there is a theorem called the vertical angles congruence theorem. We tend to shorten this as VAT, or vertical angles theorem. And that says that each pair of vertical angles are congruent. So knowing that angle 1 and 3 are vertical angles, I know 1 is congruent to 3, and 2 and 4 are also equal to each other. Okay, paragraph proof. Proving vertical angles congruence theorem. This one says, use the given paragraph proof to write a 2-column proof of the vertical angles congruence theorem. Given angle 5 and 7 are vertical angles, prove angle 5 is congruent to angle 7. Now the paragraph proof says if they're vertical angles formed by intersecting lines and they're a linear pair, and I know they're a linear pair because they form that line. 5 and 6 are a linear pair, 6 and 7 are a linear pair. Then the linear pair postulate says they're both supplementary, and since they are both supplementary to the same angle or to congruent angles, they would be congruent. Now let's fill out the statement and reason, or the 2-column proof here. Number 1 says 5 and 7 are vertical angles, and we know this from the picture, which means we're using the definition of vertical angles. 2 says 5 and 6 are a linear pair, and 6 and 7 are a linear pair. Because we're using this picture here and the definition of the linear pair, that's what my reason would be, definition of linear pair. 3 says they are supplementary. So because they are linear pairs, it means they are supplementary, and that is the linear pair postulate. Linear pair postulate, we're going to abbreviate that as LPP. And 4, if 5 and 6 are supplementary and 6 and 7 are supplementary, then 5 is equal or congruent to angle 7. This is your congruent supplements theorem. The good news is you no longer have to ever explain that all the way out. You can simply say that they are congruent based on vertical angles theorem. All right, this one is back to algebra. So finding the value of x. These two angles are vertical angles. And because they're vertical angles, they are congruent. So I can say 3x plus 1 equals 148. I can subtract 1 from both sides. 3x equals 147. Divide both sides by 3. 147 divided by 3 would be 949. And last slide, example 7, classify each statement as true or false. Number 1 says if the measure of angle 1, A plus B plus C is 180, then angles A, B, and C are supplementary. So this is kind of a trick question because they are 180 degrees. The trick here is that supplementary angles are just a single pair of angles. So this is false because there are more than 2 angles making up that 3. 2 vertical angles have the same measure. This is true. All vertical angles are congruent. and 3 if the measure of angle, if 1 and 2 are vertical angles and the measure of angle 1 is 2x plus 8 and 2 is 3x plus 4, then x equals 14. Well, we got to do a little bit of work to get to this one. If 1 and 2 are vertical angles, it means they're equal. So 2x plus 8 would equal 3x plus 4. And then subtract your 2x. 8 would equal x plus 4. Subtract your 4. And x would equal 4, not 14. So this one's false. All right, that wraps up the end of chapter 2.